to understand how this spike in carbon isotope happens, you need to understand something about the carbon isotope in the ocean, the cycle of carbon in the ocean. In the top ocean, we have a lot of productivity, a lot of photosynthesis. Now, this photosynthesis consumes the lighter carbon because it's easier to incorporate the lighter carbon into organic tissues. If you consume the organic carbon into the organic tissues, by implication, the waters around you, the carbonate pool or the inorganic carbon pool becomes heavier. So the shells of planktic forms that live in the surface of the ocean will tend to have a more positive carbon isotope value than the organic matter. Now that organic matter, of course, will be eaten by other organisms and eventually it will sink. Usually it sinks as fecal pellets. That's known as packaging. That's the technical term for it. And that fecal pellet sinks through the water column. When it gets to the bottom of the water column, it consumes the oxygen by oxidizing the organic matter and releasing some of that carbon back into the water. So typically the deep water are actually lighter in carbon isotopes because of that export of the light carbon isotope that is produced in the surface ocean. So the deep water are characterized by this much lighter carbon isotope value. And if you look at this figure here, you can see that in the Cretaceous, at the very base of the plot, we have the surface ocean. That's basically a record of microfossils, so that's a carbonate record. And as I've explained, the surface dwelling forams essentially have a very heavy delta C13 because all the C12 has been consumed by photosynthesis. However, the species that live in the intermediate and deep ocean tend to have a lighter delta C13 signature because of this respiration of the organic carbon that was sinking through the water column and gets oxidized and release the C12 in the water. And that's typical of the ocean. That's what you would observe in the ocean today. Now, once we go to the Cretaceous tertiary boundary, we have the extinction event right here. But then we go into what is known as the Strangelove Ocean. What is the Strangelove Ocean? Well, look at this. The surface dwelling forams, all of a sudden, their carbon isotope shifts to 0 or to, let's say, 1.5, to much lighter values. By extension, or by contrast, if you want, the deep dwelling species, their value shifts now to more heavy values. So it's just as if during the Strangelove Ocean, the production of light carbon in the surface ocean was drastically reduced. And so the export of carbon to the deep ocean no longer existed. Now we have an ocean that is completely not stratified, completely homogeneous in terms of carbon isotope values from the surface to the bottom. And that's exactly the interpretation here. The interpretation is that the impact of the bolide, the meteorite, essentially ceased all production in the ocean, or most production in the ocean, and you no longer have this packaging and export production of shallow water photosynthesis to the deep ocean. And that's in part because we went into what is known as a nuclear winter, with a lot of dust in the atmosphere blocking sunlight. And of course, then in the Danube we have a recovery, and we see that the surface water becomes heavier, so that's a resumption of photosynthesis. Meanwhile, the deeper water again become more negative because we have export of light carbon. But notice that the recovery is not complete. The surface ocean is never as heavy in terms of delta C13 as it was in the Cretaceous, and the deep ocean never becomes as light. And that's the Strangelove Ocean. So now you think that in modern stratigraphy there no longer are any room for controversies the way we would have controversies in the 19th century, like Cedric and Murchison. But that's not completely true, because sometimes correlation can be tricky. So here we're looking at a correlation of the KT boundary in the Gulf of Mexico, from Bass River, which is in New Jersey on the left, to Blake Nose, which is in the northwest Atlantic, and the Demerara Rise, which is in the middle of the Atlantic. And you can see here that one of the issues is that we have fairly thick interval of the KT transition boundary where we find those spheral layers. And you remember the map I showed you, That's expected because we're close from the impact. So we have a lot of spherules and we can actually correlate this. But the problem becomes more acute when you look at the detail of those sediments. And Gerta Keller and co-author in 2002 did exactly that. They looked at the detail of the section in the Gulf of Mexico, and in particular in Mexico. And they found actually several layers of spherules. So you have one layer here at the base that represented in this dark gray material, but you have 4 layers in total of those spherules. So their interpretation was, could that actually indicate multiple impacts? Can we be looking at not one impact of a meteorite, but several impacts that came in close proximity because maybe it was a meteorite shower? And that paper really threw the whole scientific world in turmoil because this was a big debate at the time. Did we have only one impact? Did we have multiple impact? Did we have maybe multiple impact and volcanism? What exactly caused the end of the dinosaurs and the rise of the mammals? Well, the answer to the question actually lies in an industry well that was drilled by Pemex, the Yax-1 well, which is right at the edge. If you look at this beautiful concentric circle right at the edge of the Chicxulub impact crater. And to make a long story short, in this particular well, you see lots of evidence for cross-stratification linked to storm deposits. And this is right after the impact. You have evidence for storm deposit. In fact, you have evidence for mega tsunami. So from this well and from this sedimentology, we understood that after the impact, what happened is you had a ton of tsunami deposits being formed close to the impact crater, which makes total sense. If you imagine the power of this impact would have a tremendous impact on the ocean. So now the conventional stratigraphy is to say that if you look at El Kef in Tunisia, the base of the ejecta layer there is only represented by the red iridium-rich layer, whereas in the Gulf of Mexico, the layer itself is several meters thick. And because it represents tsunami deposits, it's really mixed. You have several layers of ejecta deposits mixed with marine sediments and linked again with ejecta deposits. And that's why the confusion existed for a few years, where some author said, well, maybe we have multiple impact because we have ejecta deposits mixed with marine sediments, whereas other authors said, no, it's only one impact, we have one impact crater, it cannot be multiple impacts. And as you can see, good stratigraphy and good sedimentology are key to resolve these issues in Earth's history. And this is the end of this particular lecture, and it is also the end of this online course. I hope to see you in another one of my online classes, and of course, maybe one day on the GKU or the JOIDES resolution.